Okay, James. Good to have you here.
It's good to be here, Adam. Graduate House, Melbourne.
Yeah.
Go on.
So, do you first want to tell me a bit about yourself and your background?
Other than what you already know, I've had a fairly undistinguished academic career. I originally went to Monash, dropped out of Monash, but then I got involved in a lot of industrial projects, which I worked through for many years, which got me quite involved in AI, working for companies like IBIS, which you know about, where you're doing the economic forecasting systems that were used in the major banks at the time. And then subsequent to that, I decided, after having employed lots of young guys straight out of uni, that I'd better go and get myself qualified. So I did some third-year subjects to complete. And then I did a master's, which then brought me into the mining industry, my thesis. And so for the next several years, I was involved in autonomous vehicles in use in underground mines. We developed the systems in conjunction with Western Mining, which later became BHP, and that are now used in mines all over the world. And my company was subsequently sold to Caterpillar, and now I'm still working as a consultant in the mining industry in robotics, and I have a few other projects on the way, also AI related, and I am also now endeavouring to finish my PhD, as you're aware, in machine consciousness, whether we can give a machine an inner experience of existence the same as we have.
Okay, that's good. So, what got you involved or interested in AI and robotics and mining?
Oh, I don't know, I think it was Astro Boy.
Astro Boy.
Astro Boy, he was fantastic. He had little rockets on his feet.
Mm-hmm.
So, no, it's one of those things when you're young, you just, something takes you fancy, and there's always a niche, and social pressures make you go into the niche, and I was the mad scientist, that's all, and so everything to do with science fell within my purview, and so and you naturally find the most interesting areas of that and pursue them, and robotics was one of those areas.
Okay. So there's been a few changes in the world over the last few decades since your interest in technology. What do you think has been the most influential impacts that science or technology has had?
I think of recent times would have to be the internet.
Mm-hmm.
But the internet is really been able to bring together areas of knowledge from lots of disparate areas, so it's been a great boon to scientific development in all areas. Just the ability to go online, look at other papers quickly. Mm. It's sped up the process of academic research phenomenally, and so I would have to say that the internet would be the biggest single advance. Now, of course, the internet itself has been enabled by a myriad of technologies underlying it, some of which are straight algorithms, many of which would hark back to the transistor, which was invented about the same time I was born, back in '56.
So which of these technologies would you find the most interesting, which have been, what have got you interested in technology? If there was a few technologies which you saw, which of those would you say you found the most interesting, and the ones which sort of influenced you, other than Astro Boy, to become an AI and an engineer, an AI expert and an engineer?
If you take the amount of time that you spend using a particular form of technology, again, the internet just wins hands down. Mm. And the thing about the internet is, because we as humans are all the time looking at, say, other people, for instance, we find people interesting, we're biologically predisposed to find other people interesting. The thing about the internet is that it brings together information from all venues, all walks, and therefore it is by definition interesting, because whatever you're interested in is on the internet and can be looked at. So again, it has to be the internet, hands down.
Okay, right. That's good. But I was kind of fishing for something AI related, but anyway, it doesn't matter. So anyway, well, how about I put this question to you. How has AI changed in the last 10 to 30 years, or 15 to 30 years, and what's the same?
The biggest change in AI that's taken place in the last 20 years is that people have given up trying to define the problems that they wish to solve. So when I say given up, they've realized that the problems could often be so complex that we may not know a solution, but yet we can still develop systems that can function in those environments. And when I say we will not know a solution, we have developed systems in the last 20 years that evolve solutions. So I think the biggest change has been this idea of utilizing the evolutionary paradigm within artificial intelligence, where we realize that problems don't have to be fully described. Rather, we can develop systems that learn to solve those problems without us actually knowing the answers ourselves. Sure, we may know the answers once the systems have learned to solve them, or we may know a solution. But this is a very different paradigm to the original, which was very much, and this came out of Minsky School, of course, which was very much define the problem. This is the problem. This is the subcomponents of the problem, and we will build systems that operate within these boundaries that will solve that problem. We were very good at doing that so long as we could understand the problem. But what happened was we found many real world problems were just beyond us, too complex, there were too many subtleties, too many variables. So by developing systems that operate in an evolutionary paradigm, we've now managed to develop systems that can drive vehicles, that can autopilot aircraft, or in my case, can drive complex pieces of hydraulic machinery underground. So that acceptance of evolutionary paradigms is, I believe, the biggest change that we've seen in AI.
You've spoke about evolved neural nets before. Can you explain what they are and how they are different from something like an expert system?
Well, a neural network is in its simplest learning incarnation a type of gradient descent. It simply adapts itself to find the best solution, so that you give it patterns, you destructively reinforce it when it gets it wrong, you positively reinforce it when it gets it right, until it more often gets it right than wrong. That's an evolutionary paradigm in itself. So neural nets have endemic to their operation a type of evolutionary paradigm, but you can then go to a meta paradigm beyond it, which is to change the structure of the network and to change the actual types of neurons, or neurodes in this case, and the interconnections between them, in the same way that nature will specialize in componentry. Our brains are not just one thing. Our brains consist of a myriad of sub-brains, each one of which is architecturally adept at solving a certain class of problems by evolution. They have evolved to be adept at that, and because they've been functional and have a utilitarian value, they've been maintained within our brains. And that specialization of parts of the brain is a very efficient process. It's much more efficient to encapsulate in hardware and architecture a problem than it is to try and do the whole thing in software. So the brain has, over time, developed specialization for sub-aspects of itself. In some cases, of course, they simply evolved in situ. That is, they became more and more complex in relation to the others. So it's not like you had one structure that then specialized in a myriad of places. You had lots of subclusters that all specialized in different componentry as the brain evolved. But this specialization is something that we don't generally do in neural nets. We do it a little bit, like in my own experience, for instance, we had neural networks that were doing formal linearization on hydraulics. Now you can see that as a specialized cluster of neural nets, and they were then integrated into the larger neural net, which was doing some other aspects of navigation and predictive interpretation of data and working out where the system would be after a certain input had been put in within a certain number of milliseconds. Now, so the addition of specialized neural nets, that subspecialization is a critical aspect that has come about through evolutionary processes in the evolution of the brain, and that we're now starting to develop in our own artificial neural nets. So instead of just trying to build one gargantuan neural net, we're saying, oh, we can do better at this if say, our audio processing might have its own sub-neural net, which is architectured differently and specific to that task.
Okay, so you can have many sub-neural nets that are perhaps controlled by some sort of model view controller mechanism, like an observer mechanism, whether that be a neural net or some sort of expert system.
Some kind of meta paradigm. But on this same thing, I have to say that the Church-Turing hypothesis applies, that a lot of those subnets are themselves computable in terms of the larger nets. They can be emulated by the larger nets, but just not as efficiently.
Okay. So what is it about the... Okay, do you think there's enough funding being pushed into the development of artificial intelligence, or pushing towards this general aspect of artificial intelligence that we are looking for? Do you think there should be more funding?
General intelligence?
Yes, maybe we should explain what artificial general intelligence is.
I think the amount of funding is the amount of funding. Remember that neural nets, or AI in general, is being developed because of a socioeconomic need. That is, sure, there is some pure research being done on this, but by far most of it's done by people like stock traders, etc., saying, oh, well, we want a competitive advantage here, or people such as our industry who have said, look, we want to make this safer. We don't want humans in that environment, so we want to do something to automate and take people out of that environment. Or ultimately, it's we want to do a process more efficiently or faster. So the funding for AI is generally economic. That is, can we do that problem more efficiently? Can we do, say, a triage problem more efficiently than a team of medicos in a hospital? Can we, and of course, generally the answer is no, but when you're talking about people who've been working 3 shifts back to back, there might be some crisis underway, there might be some epidemic. The answer starts to become yes, because our systems, whilst they may not perform at this stage to the same level as human experts, they will perform consistently and at times will outperform, therefore, the human counterparts. Now, the consequence to this is that where there is money to be made, or lives to be saved, or processes to be performed that are very difficult to have humans perform them because of environmental processes, etc., then we're applying AI. But the concept of artificial general intelligence, which is what you were alluding to, is directly competitive to a human as a whole. And when you realize that a human is pretty cheap to manufacture, right, they take maybe, in a technologically advanced society like ours, it takes between $500,000 to $1 million to program them up, to get them to year 12, right? So let's say that takes about $500,000. So nothing to create the basic structure, $500,000 to get it to a functional, general operating system. And that's a robotics platform. That's not just a smart system, that's a system that's integrated into its own kinetic device. It can do things. That's a pretty hard thing to beat. Right?
It does take a long time. I mean, that's 20 years. 20 years.
Yeah, that was in the cost, that period, over a period of time. You start early, they start popping out in 20 years' time, ready to go. right? But it's hard to beat. And the point is, and what we're seeing now is, of course, we're saying, oh well, can we make cheaper ones of these? Can we make cheaper people? And the solution to making cheaper people isn't to go off into a lab and build a robot that emulates that person. It's to go to China or to go to India where the people are cheaper, right? Still educated.
Is that going to be the same in 20 years?
Possibly not. And at some point in 20 years, as technology improves, yes, it'll be cheaper to go into a lab and start producing AI systems. Or what will probably happen, I suspect, is we'll simply take all the thousands and thousands of AI systems we have out there and start plugging them into each other till we start to get a more generally capable system. And then we'll start to see it sort of seeding on itself, because it's now got the ability to cross-pollinate ideas between different disciplines, whereas at the moment most AIs are specific to the task. They can fly an aircraft, but they can't take the rubbish out, that sort of thing.
Yeah, that's true. Okay, but yeah, so how would one, if you have many specific AIs sort of bunched in together, first you'd need a system which could interpret the inputs and outputs of all those AIs, and then the cross-learning capability would be very difficult as well, because one AI programmed to learn chess coupled with another AI programmed to learn checkers wouldn't necessarily be able to learn Chinese checkers just by merging the two. You'd need something to be able to interpret and move the rules from those games over into a different paradigm, wouldn't you?
No, you'd have a Chinese checkers playing AI, and you simply plug into it. And if the problem called for a Chinese checkers or Chinese checkers-like problem solving, you would simply ask that sub-part of the AI what to do. And it would say, well, I recommend, based on my experience of Chinese checkers, that you do this at this particular point.
Would it then be able to learn new ideas, or perhaps new games that it hadn't encountered before, or adapt to new, different scenarios in the world around it?
Well, of course, the more sub-AIs that have been glued together, the more it's got a wider domain of problem-solving ability. And when a new problem occurs, say Go, it's got to learn, it's got to understand the rules of the game, but some of the concepts that it's learned from the other games are surely going to apply.
Yeah, sure. And so wouldn't, by definition, then the artificial intelligence be general enough to take concepts from one particular domain and move them into another?
Yes, it may be, but it depends on the domain, and it depends, of course, on the underlying reality of the problem. That if I can only take paradigms that I've learnt if they're applicable to the new paradigm. One of the biggest problems we have is false applicability. The old, if all you've got is a hammer, everything looks like a nail. If all you can do is play chess, then everything looks like a chess game, and that's of course not necessarily true. So the broader your experience in life as a person, generally the more competent you are at new problems, because you can relate something in your repertoire, in your history, to the problem at hand. And so it's the same with AI.
So what research fields do you think will be successful within the AGI R&D? What streams of research or R&D would be successful in being the most successful in generating a strong artificial intelligence?
My belief on this is that it's going to be processor speed and massive parallelism. So I see a brute force approach that, as I've said to you before, I see it, this is very much an example of the frog climbing the stairs. If it can get up a 9-inch riser, it can climb the whole staircase. If it can only jump to 8-inch, it's always stuck on the first step. But fundamentally, the frog is the same thing. And I see a similar thing happening here, that the ramifications of the Church-Turing hypothesis are that if we can compute it, and we can compute it faster, then we can ultimately solve it. It might take a long time, but the problem is, if it's computable, then we can compute it with a particular architecture of machines. So therefore, what we should be doing is expanding our evolutionary learning algorithms, our platforms on which those algorithms sit, giving them more computational power, making them faster, making them bigger, and I think we'll then start to see solutions. And once we get solutions, of course, then as a form of heuristic, we simply specialize. We then reductionalize the system, work out how it solved the problem, and determine better architectures that may solve it faster. And then we will start to specialize for, and that's just done for economic reasons.
Okay.
But I think that the core answer to your question is processor speed. Just let Moore's law do its work.
So where? Okay, can you explain the difference between? No. Okay. So can you explain the Turing hypothesis?
Okay. Many words.
And how that will we be able to do everything we need within the von Neumann architecture, or do we really need to parallel as much as we do in the brain? I mean, there's billions of connections between all the neurons as well. Do we need to simulate those?
No. Look, I'll pass on describing the Church-Turing hypothesis, other than to say that it's whether systems are computable, whether things can be computed, can be solved. And one of the consequences is that there is nothing in a massively parallel system that cannot be done in a single processor system just over a longer period of time. And this is a very important recognition. A lot of people see parallelism as some kind of panacea that's going to suddenly, that AI is going to suddenly emerge because of parallelism. No, parallelism just gives you speed, but it doesn't give you any unique computation. Unless you were to bring in, say, quantum mechanics or something, and then you can argue that there are some unique characteristics of parallel systems. But without that, in a straight Turing architecture, parallelism doesn't give you anything special. It doesn't suddenly create some kind of new emergent paradigm. It just doesn't happen. Parallelism is just a single processor done multiple times, and so it allows you to do the problem faster, and it's also got a lot of advantages in terms of manufacturing, because it makes sense to, when you've got a monolithic block of silicon, to put multiple processors on it and thus end up with a parallel system. But that said, I mean, I see the recent developments of cloud computing as being phenomenally advantageous to the work in AI. The ability to go online and pull down several thousand virtual PCs. Pull down several thousand virtual PCs is now you can do off the Amazon cloud. And on those you can run your neural nets or whatever particular AI paradigm you're doing, or even more fundamentally, search algorithms, just breadth and depth first search algorithms, nothing, just brute force algorithms to solve problems. Now, that capability, which has also come from the internet, and is, I think you'll find that's where the real grunt work of AI is now going to be done.
Okay, cool. So you mentioned quantum computers. So where are we at with quantum computers, and where do you see some possible breakthroughs in the future?
Well, again, the biggest problem with quantum computers is scale. I think they've managed to get 2 or 3 qubits now stable, and they've managed to factorize 15. As a couple of years ago, they managed to using Shor's algorithm, managed to factorize 15. Well, that's pretty impressive. But of course, the thing about quantum computers is they will, once you start getting any decent number of qubits, they become computationally exponential in power, and certainly leave everything else behind it. But of course, they are hideously difficult to maintain the coherent state that's required. And but there's a lot of good work being done on it, and there might be even some left field paradigm shift that will allow us to do it. You may recall some people working on computation within liquids, within liquids, quantum computation within liquids.
Or topological quantum computing.
Topological quantum computers, yes. So there may be some paradigm shifts in the industry, but ultimately quantum computers will effectively accelerate. They'll break Moore's law on the upside if they ever come into play. So they may also, quantum computers, of course, as we develop them, we develop a deeper understanding of how the universe itself works, that we live in a conception that our world is a physical world, atoms and solid things and concepts relating to them, of course, but quantum computers don't live in that world. They live in a world of Schrödinger wave equations, which see the world in a different light. Things are not as solid and tangible as our concepts of them are. Things really are fuzzy. Things are superimposed. There is no ultimate nature of reality that we perceive in a quantum world. And so the development of quantum computers will give us more of an understanding of that world, and may actually give us more of an insight into the phenomena of consciousness itself, which, as you know, is an area that I'm interested in. That concept of consciousness being a quantum mechanical thing has fallen out of favour over recent years, of course. But I think you'll find it'll come back. That I think you'll find those early physicists, when they looked upon the observer, the conscious observer, as being a very fundamental part of what quantum computing was, that when they talked about the observer, they meant conscious observer. And why people like von Neumann, etc., were so interested in consciousness. I remember von Neumann's background. He was a physicist before he went off and did economics in his spare time and solved various. But I think you'll find that some of those early physicists who were subsequently chastised somewhat for extending their brief and making comments into areas that philosophers felt was their domain, I think you'll find that they'll be shown to be right, and that consciousness is in some way linked with quantum mechanics. But that's just a personal belief of mine.
Okay, cool. So it's interesting that a lot of people are a bit sort of skeptical of any computer being able to think generally, or maybe not even like a human, but maybe like a human, or maybe like a, at least an intelligent problem-solving and creative entity. They seem to think they have a knee-jerk skepticism, or that it's even impolite to even talk about these sorts, or think about these sorts of things. So what are your views on the reasons why people
I think the Turing test is a bad idea. That I think that as computational power increases, and as our understanding and our ability to emulate functions within the brain improve, we're going to see machines that will pass the Turing test. I mean, we already see machines that can pass the Turing test for seconds, clearly. A tape recorder could pass the Turing test for 5 seconds by simply pushing the right button and saying the right thing. And you would think, oh, that sounds good. If it was coming from behind the screen, you couldn't say it was a tape recorder.
Some people have deceiving answering machine messages that do just that.
Correct. And a very good point that answering machine messages sometimes do fool you, that you will launch into a dialogue with a machine. But of course, the idea of getting to do it for half an hour or an hour, well, currently beyond, well, certainly beyond the concept of what computation was when Alan Turing put forward the Turing test. But it's going to be passed soon, and it's going to be passed soon by a machine not dissimilar to a tape recorder, just a lot bigger with a lot more buttons. And those buttons are being pushed by various social cues based on inflection of your voice, the words that you've spoken, the environment it finds itself in. But that passing of the Turing test, I think, hasn't created a machine there that's conscious. It's simply created a machine that's able to mimic you, or mimic answers that you want to hear. And so I think, in terms of what we define as intelligence, the Turing test might work, or even social intelligence, but it fails when it comes down to consciousness. There is no reason why a tape recorder would ever be conscious. And whether or not a tape recorder was to pass the Turing test, now just a tape recorder of the complexity of your average single button Sanyo tape recorder or answering machine, it could pass the Turing test now if it was lucky. It'd have to be phenomenally lucky to do it if it had a message recorded on it that just happened to match the dialogue that was being given to it. But it could pass if it was lucky. And I don't like that kind of objective test that can be passed on sheer luck. So I don't think there'd be anyone suggesting that a tape recorder is in any way conscious, right? Particularly if we made it, say, just to make it even more complicated, a wire tape recorder. So it's a purely mechanical device. I don't think that anyone would argue that such a thing is conscious, even though it could be lucky enough to pass a Turing test at some point. And similarly then, imagine 10,000 mechanical tape recorders side by side, thus more likely to pass the Turing test if we simply had another mechanism pushing the appropriate button at the appropriate time. I don't think that is in any way going to provide us what we really want out of the Turing test, which is to say, hey, that's like us. It's conscious. It has an inner experience of being. It has beliefs, desires, goals, motivations. I don't think the Turing test will ever answer that for us, but there's a little bit of a misconception that it does.
Okay. And what is that misconception based on, do you think?
Oh, I think it's just, at the core level, it's just this confusion in the mind of many people between intelligence and consciousness. That it is possible to be highly intelligent and unconscious, as is most of your brain at any one time, doing very clever things to run your body, but totally unconscious.
Okay. People seem to me to be a bit short-sighted when it comes to looking at technology or the way science has been progressing. And I see that there could be quite some benefit in looking at long-term approaches, or looking at how there might be some overlapping technologies which will help the growth of technology in various ways. So the question is it important to think about the future of technology and science today? Think about it like 10, 20, 30 years in advance? Are we doing that well?
It's important to think about the direction it's going, because there are some clear dangers in some technologies. If I was to invent a super atom bomb, for instance, I wouldn't necessarily want that technology to be promulgated so that everyone had one. So given that technology is generally an enabler on a smaller and smaller scale, that technology tends to increase the amount of power given to smaller and smaller groups, we have to monitor it. We have to monitor the direction it's going, because there is inherent dangers within it.
Or like biohackery, or somebody being able to create a nuclear bomb from...
Correct, and there's dangers
Scrap.
that we, as we sit here, do not know. As Karl Popper said, we cannot know today what we will discover tomorrow. But we can at least monitor what work we're doing and turn as many minds as we can to the problem, so that we can have an informed opinion about it and have informed discussion.
Is there any future crossroads in science and technology that you see as having big impacts?
Quantum computing, obviously, the biggest horizon disruptor of our society would be some form of artificial general intelligence, because the Industrial Revolution, which managed to push everyone out of the country into the cities, if it was to happen again, there's nowhere else to go. That our muscles were replaced by steam engines, basically. So if our minds were replaced by another machine, it's going to have enormous social ramifications on society. Work disappears as we know it. Now, that doesn't in any way, I'm not in any way trying to describe a dystopian future with that. I'm simply saying it's one we have to consider, that there really does become less and less jobs, that when we look to the future, at some point there is no jobs for us, which is, of course, ironically, a Marxist utopia.
Post-scarcity, post-jobless society.
But so I think that the most significant on the horizon technological development will be artificial general intelligence. Now, and because I believe that that will come into existence simply because of Moore's law, it doesn't require any more paradigm understanding, etc. It really just requires more processing power with evolutionary learning algorithms aimed at a particular task. And when we get to a large enough size, I believe that the problem will become tractable, and we'll be able to have systems that demonstrate a general form of intelligence, competitive to and soon surpassing our own. Now, the social dislocation caused by that will be immense. I mean, at the same time, it could be a great world to live in. Everyone wants to retire early, but would everyone want to retire early if everyone was retired? It's an enormous social can of worms, what to do about it. And because the world is still too fragmented, it's going to happen. It's not like the government can step in and stop it. If it doesn't happen here, it will happen in other countries, because the advantage of smarter computers that you can talk to, if you like, and that can answer the questions in a human way, will give them such an advantage that the others cannot afford to be left behind economically. So in our modern fractured world, it's going to happen. And I think it's going to happen sooner than people realise. A lot of discussion has been the complexity of the human brain. People have said, look, it's so complex and it's so massive that we will never understand it. We will never make a system that will do it. I think those people are forgetting that a large part of the complexity of the human brain is to do with things like running the cells, dividing, multiplying. The human brain is a system in its own right. It has to be self-perpetuating. It has to organise its own energy supply, it has so many parts of it that we can streamline by going to silicon. We don't need to worry about how do you make a cell self-perpetuating. How do we have we don't have to worry about fighting off viruses, or ironically we do, but not quite the same. We don't have to worry about scaffolding problems, etc., because we can solve those problems with material science in ways that were not possible through an evolutionary search. Nature had a hard enough time, say, coming out with a free spinning wheel simply because it couldn't get blood flow across it. It could get ball sockets and things like that, but you don't often see free spinning wheels in nature. You see things like some animals roll in balls, that's true, but you name an animal that has wheels attached, I don't think you'll find one. It just doesn't. And there's a reason for that, and that's simply because it's a very difficult problem to get a blood flow across a free spinning wheel, and it was never solved by nature, right? Oh, that's not true. I suppose some of the flagellum on bacteria could be considered to be free spinning wheels.
But do they have blood? Do they have blood? I don't think so.
They don't have a blood supply across them. They don't need it. They're too small. They're just proteins on one side or the other. But they are free spinning. So, but we see free spinning wheels everywhere. We look out the window because they're an incredible efficient way of making transport. And the same way, when we build silicon-based chips, we don't have to worry about how these things are going to self-perpetuate because we've got lithography. We just print the things. So a lot of the complexity of the human brain is not required for the core part of the problem, which is intelligence. And so when people talk about the number of petaflops, and I think the current count is about 8 petaflops of calculation going on in the human brain, most of that is not being applied to the tasks that we would consider what we want to see solved in artificial general intelligence. And as such, I tend to think we have already exceeded in our larger supercomputers the processing power required to run an artificial general intelligence system. But once we configure that into, say, a neural network, the efficiency of that software paradigm, of course, drops us much below that level. Not too far below, but below that level. And so, we go back to the old frog climbing the stairs, not quite enough yet to produce what we want to see, the artificial general system that can mimic and communicate with us as we're doing. But it will happen, and I think it will happen quickly, far faster than people realise.
Okay, have you got a date on that? Do you want to
add? I'm not going to be drawn into a date, because we don't know today what we will discover tomorrow. Right? We've always had a sense of technological optimism, that we've always felt that AI is just around the corner. But that's because we couldn't see the problems that are going to come up. And the same can be true now. There may be problems that are going to come up that we just do not see where we are. If I'm correct, and if church Turing can be applied, and it's really just a matter of making a bigger network, then we will, and Moore's law maintains. Remember, Moore's law may not maintain. It's been working pretty well to date, but a problem may occur. Quantum computers may not eventuate. Moore's law might flatten off next year. And if that happens, of course, we may not get to the side. It may not be economically feasible to be building computers with the size and complexity necessary to emulate human brain. and certainly not cheaper than it is to go and make one yourself and send them to high school and then put them out in the workforce 20 years later.
Ray Kurzweil and a number of others advocate the pathway to artificial general intelligence through reverse engineering the human brain, or a brain, and synthesizing that brain in some form of artificial environment. Do you think there would be, first of all, do you think that that will work?
Yes, I think it would work. If you could reverse engineer the human brain, I think you would end up with something that was human brain-like. So I think that would work, but
would you be able to take it
I
further?
personally don't think it's necessary.
Okay.
I think we just need bigger, larger neural networks.